Lizzy Ferguson, and I'm going to be talking about math and music tonight. And so a little bit about me. I have been playing music all my life. I played classical violin since I was 4, and currently I'm in the MA acoustic band playing violin, mandolin, and guitar. So when I was looking for a topic to present here, it seemed pretty natural to follow my passions and explore the relationship between math and music. And at first glance, these two might seem really different. Math is very focused, very analytical, and music can be much more creative and abstract at times, but really, when you look at them, the connections between them are endless. Math is in harmonics, in time signatures, in basically everything, and even the Fibonacci sequence pops up in songs sometimes. And it would really take me much longer than 15 minutes to present on this, so I decided to focus down on one topic, which is may seem pretty simple, pretty trivial, but I promise it's a lot more complicated than you might think, and that problem is how to tune a piano. That's supposed to say how to tune a piano. Why not? So how many of you have ever played piano? How many of you might have a piano in your home? Yeah, so it's a pretty common instrument. And what intrigued me about this problem is that for the 10 plus years I've been playing the instrument, I never knew that there was actually a lot of math going on behind it, going on inside with all the tunings of all the strings. And it was pretty fascinating because I'm sure some of you have seen a piano tuner come in and fiddle with all the strings. And I didn't know how it worked. I'm probably sure you guys probably don't know how it works either. And it's pretty fascinating because there's so much math that goes on behind it. And hopefully with this presentation, you'll get a little insight into that complexity. So before I get into the problem, I'm going to have to give you a bit of a history lesson. So as I said before, math and music are very closely intertwined, and this relationship actually goes back a very long time to the 6th century BC with this lovely gentleman right here, the Greek philosopher Pythagoras, who, among other mathematical discoveries such as the Pythagorean theorem, discovered the relationships between numbers, so math, and sound, music. And this wasn't exactly a surprise because he thought that numbers rule the universe, but it was significant nonetheless, and what he discovered was actually a set of simple ratios relating harmonizing tones, and today we call this the harmonic series. And so take a string, say a guitar string, it's fixed at 2 ends, so when you play it, it oscillates, it vibrates in a wave, and this is a sine wave. And I know this is only half of a sine wave, but we're just going to go with it right now. And this wave, it vibrates, or the rate at which it vibrates is called the frequency, so we're going to call that F1, so that's going to be the fundamental frequency. But when you hear this frequency, you also hear a set of overtones. So an overtone is precisely that, a tone that's played over your fundamental. So you hear this fundamental in red, you also hear an octave in blue, which has a frequency twice that of your fundamental, so it completes 2 iterations in the time that it takes your fundamental to complete 1. And in addition to this octave, you hear a perfect fifth in green, which has a frequency 3 times that of your fundamental. And also a perfect fifth, or perfect fourth. So in orange, a note with a frequency 4 times that of your fundamental. Also a major third in purple with a frequency 5 times that of your fundamental, and a minor third in black with a frequency 6 times that of your fundamental. And this actually theoretically should continue on forever, even though our human ear can't detect it because it's going to get so high, and it would be pretty impractical to graph it here because it would just be small and you would just see like a line. So it continues on forever, but right now we're just going to deal with this set right here. And what Pythagoras discovered was a set of ratios relating these tones, between the frequencies of the tones. So between the fundamental and the octave, their frequencies is a ratio of 2 to 1. Between a perfect fifth and an octave, the ratio between their frequency is 3 to 2. Between a perfect fourth and a perfect fifth, there's a ratio of 4 thirds. Between a major third and perfect fourth, ratio of 5 fourths. Between a minor third and a major third, a frequency of 6 fifths. And this difference between the harmonizing tones can also be quantified using musical intervals. So here we're going to be using semitones. For those of you who know music, a semitone is just a half step. For those of you who have no idea what a half step is, basically a semitone is 1 step up in a normal scale. So our Western scale goes A sharp, B sharp, all the way up to G and G sharp. And a semitone is just basically the distance between one note and the next, so A to A sharp, for instance. So an octave, for example, spans 12 semitones, a perfect fifth spans 7, perfect fourth spans 5, major third 4, minor third 3, and you don't have to memorize those. I know them, and this will come up later in the presentation. And for those of you who are more visual, you can see this is a set of harmonic tones on a piano. So you have your ratios between your frequencies here and also your semitones shown. And basically, to sum it all up, harmonic series is a set of infinite overtones, we're only going to use these for now, with a set of ratios between the frequencies and can be quantized with semitones. So we're going to get back to the problem now, how is any of this relevant to tuning a piano? And harmonic series is actually used in tuning instruments. So you can take a harmonic on one string and match it to the same pitch harmonic on the next string up. And you can repeat that for however many strings you have, and your instrument will be tuned. And this is pretty practical with instruments such as the guitar and violin because there's only 6 strings and only 4 strings. But when you hit the piano, you get kind of a problem because there's so many strings, because you have 12 keys, so the 12 notes in a normal scale, and you have 7 of each of those in different pitches, plus a few on both sides, so you end up with 88 individual keys, 88 individual notes with individual frequencies that you have to tune all perfectly together. And that's going to pose kind of a problem, but we'll get to that later. So when we're tuning the piano, basically you want to think back to those harmonic ratios that we already talked about, specifically the one between the fundamental and the octave. So we're going to start off at this C over here, we're going to call that C1, and that's going to have a frequency of F, so that's going to be our fundamental frequency. And what we're going to focus on is the relationship between the fundamental and the octave, so we can move an octave up, which is 12 semitones, to our next C, we're going to call that C2, and because the ratio between the fundamental and the octave should be 1 to 2, the frequency of this C2 should be 2F. And this isn't just limited to one octave, it's actually apparent in the entire keyboard. So you start off with your fundamental, C1, you move up an octave to C2, which needs to have that 1 to 2 ratio, so the frequency is 2F. An octave up from C3, or C2 is C3, which needs to have that 1 to 2 ratio with C2, so that frequency is 4F, which an octave up from C3 is going to be C4, and you have to, that frequency has to be double that of the note of the octave before, so that's going to be 8F. C5 is going to be have a frequency double that of the one before, so 16F. You might see a pattern. We're just increasing. We're just doubling each time. So C6 is going to be 32F, C7 64, and C8 is 128F. And basically, when we're tuning the piano, what we're looking for is this magic number of 2 to however many octaves we have. And that's going to ensure that we have that perfect ratio, perfect harmonic ratio between our fundamental and our octave. So we can go ahead, hopefully you remember this, we're going to go ahead and use these ratios to try and tune the piano. So let's start off with major thirds, which has a ratio of 5/4 and spans 4 semitones. So we can go back to our piano, and we can increase in intervals of 4 semitones, so from C to E, from E to G sharp, and then one more from G sharp to C, and so we've hit our octave. So we want that relationship between C1 and C2 to be 1 to 2, right? So we take our fundamental, and we multiply this by the ratio of a major third to get the frequency of that E. And to get the frequency of the next note, G sharp, we have to multiply it by another 5/4, the ratio of a major third, and we do that one more time to get the frequency of that C2 if we tune with major thirds. And since we've only increased 1 octave, our magic number is 2 to the first power, so just 2. So hopefully this will equal 2F, right? Well, no, it's actually equal to 1.95, which is less than 2, meaning that if we tune the piano with major thirds, our piano will be flat, or we'll hear that C to be slightly lower than what it should be. So major thirds don't work. We can go ahead and try minor thirds. So a minor third spans 3 semitones, so we increase in intervals of 3, once, twice, 3 times, and another one, and we hit our octave. So we go from C1 to C2. And we can do the same method as before, so we take our fundamental, multiply it by the ratio of a minor third, so 6/5 to get the frequency of D sharp, one more time to get the frequency of F sharp, another time to get the frequency of A, I think, and then one more time to get the frequency of our C2 if we tune with minor thirds. And we've still only increased 1 octave, so our magic number is 2 to the first, but 6/5 to the 4th power is 2.07, which is greater than 2, meaning that if we tune the piano this way, our piano would be sharp, or we'll hear that C slightly higher than what it should be. So major thirds and minor thirds don't work, so we can go ahead and try another one. Let's try perfect fourths, and you can already tell it's going to get a little more complicated, but you'll stay there. So perfect fourth spans 5 semitones, so we're going to increase in intervals of 5, and we actually miss every C up until this one here. So we take our fundamental, we multiply it by the ratio of a perfect fourth, however many times we go up. So we take our fundamental, multiply it by 4/3 12 times, which is equal to 31.569, which is nowhere near 2. But that's okay, because our magic number has changed, because we've gone up 5 octaves here. So our magic number is actually 2 to the 5th power, which is 32. But it doesn't work, because 4/3 to the 12th power is equal to 31.5, which is less than 32, meaning that if we tune the piano in this way, our piano will be flat. And you're probably going to see a pattern forming here, but let's do one more, just because, it's fun, right? So perfect fifth, we can try perfect fifth. It spans 7 semitones, so we increase up the piano by 7 semitones. We finally barely make it with that last key on the piano. We take the fundamental, multiply it by the ratio of a perfect fifth for each time, so 3/2. Our magic number here changes again because we've gone up more octaves. It's not 2, it's not 32, it's actually 2 to the 1, 2, 3, 4, 5, 6, 7th power, which is 128. And 3/2 to the 12th power is 129.7, which is greater than 128, meaning that if we tune the piano in this way, our piano will be sharp. So I actually did quite a few of these. I did 10 of them on my own. It took me a while, and it was quite infuriating because every single time I got the same 2 results, either sharp or either flat. I never hit that perfect number, that perfect 2 to however many octaves. And it was, I could have just given up there and said, okay, so it's impossible, yay, and just move on. Or I'm a little obsessed with math sometimes, and it annoyed me. I really wanted to find out why. And so I took to the interwebs, and I did some research, and I found the rational root theorem, or the corollary of it, which states that for any integers a, b, and n, where n is greater than 1, then a/b to the nth power will never equal 2. What this means is that you can take any ratio, so a/b, and multiply it by itself however many times, and you will never get 2. So you can take any of those harmonic ratios that we dealt with before, so major third, minor third, perfect fifth, perfect fourth, and you can multiply it by itself however many times, so go up however many intervals you want on the piano, and you'll never hit 2, you'll never hit that magic number, you'll never get the ratio between your fundamental and your octave to be 1 to 2. So I just threw a lot of information at you, and you're probably wondering, what does it all mean? It's okay, I'm going to boil it down to you in one statement. If you get anything out of the presentation, I hope that is this. It is mathematically impossible to tune a piano perfectly. This is probably a pretty complicated, it's weird, right? All your pianos are tuned. Oh, yes and no. They're tuned in a method that's called equal temperament. And what equal temperament does is that it doesn't use any of those clean ratios, those clean harmonic ratios that we used before. It actually creates its own. So it divides the piano into intervals of 12. So you increase 1 semitone, basically, that's your interval, until you hit that octave. And it creates its own ratio, so we can call that ratio R. So it increases 12 times, you multiply by R each time. So you take your fundamental, you multiply it by R 12 times, and you get that 2F, that perfect relationship, that perfect ratio between your fundamental and your octave. And what we've done actually here is just create a simple algebraic expression. So we can take that expression, simplify it to F times R to the 12th power is equal to 2F, divide out the F, so we get R to the 12th power is equal to 2, and do a little manipulation, and you get that ratio for equal temperament is R to the 12th root of 2. And we can actually test this ratio like we did with the other one. So we go up to the piano, we know our interval is 1 semitone, so we increase by 1 semitone until we hit our octave. We take our fundamental, multiply it by that ratio, so the 12th root of 2, 12 times. We get the 12th root of 2 to the 12th power, which is equal to 2. So we've finally gotten that ratio. From our fundamental to our octave is finally a ratio of 1 to 2. And what was kind of funny about this is that this is actually the only perfect ratio that exists on the piano, from your fundamental to your octave. All the other ratios, so your perfect fourth, your perfect fifth, so your major third, your minor third, they're all either slightly sharp or slightly flat, which is, I don't know, so your piano is tuned imperfectly perfect. Yeah, we're not all perfect, so. But what was really the amazing thing that came out of equal temperament was the ability to play any song in any key. So if you remember back, think back to the image of the piano with all the different ratios. Remember, they kept getting smaller, and that's because if you tune a piano to a specific key, all the ratios, they change. They're not stable like with equal temperament. And with equal temperament, the distance between every single note is the same. So you can play in any key and it doesn't matter because the difference between notes are always the same. And no one was more excited by this prospect than Johann Sebastian Bach, who went ahead right when this was discovered and implemented and wrote the Well-Tempered Clavier, so a set of compositions